This video will finish chapter 2, and we're moving on in our atomic structure, talking about the third subatomic particle. And so electrons are really key when we talk about chemical properties and chemical bonding. So electrons are the only subatomic particle that are involved in chemical activity. And so protons and neutrons are in the nucleus and are kind of shielded from other elements and molecules because they're hidden in. Electrons in the cloud are actually available and are part of chemical activity and chemical bonding. So electrons occur in energy levels called electron shells, if you will. There is a difference in atomic structure, and we're going to go back to a simpler version. So if you've learned about orbitals, we're going to talk about orbits. We're going to talk about a simpler arrangement. So information about the distribution of these electrons is in the periodic table. The first shell is full with 2 electrons, where the second and third are going to hold up to 8 electrons. So if we take a look at that periodic table, you can see that there are 2 elements, and then 1, 2, 8, and 8. And this is how, or this is why, the periodic table is arranged that way. It's trying to indicate how many electrons or how they are arranged. So the number of electrons in the outermost shell is the most important. Those are the ones that are most free to interact with other things. And so the number of electrons in the outermost shell determines the chemical properties of an atom. Those electrons are called valence electrons. And I know my mom on the kitchen window had a valence, like that little curtain over that's spelled differently than these ones. And so valence electrons are in the outermost shell of our atom, not my mom's kitchen window if you caught that one. The thing with atoms is that they want to fill their shells. And so there is this desire to be completed. This image is great because it illustrates out how things look. And on the periodic table, if you can imagine, there's actually a break between these two, right? Where like down below in the next column or the next rows, there's more in between there. And so this is what, just quickly illustrating the arrangement of electrons and where they are in atoms. So if we talk about hydrogen, there's 1 electron. Helium has 2, and then that one's full. When we have lithium with 3 electrons, that third electron has to bump out to the next electron shell, and they move through like this. The number of electrons is the same as the number of protons. And so chlorine down here, as atomic number 17, has 17 electrons to place. So 2 in the first shell, and then 8 more, so a total of 10. And the valence electrons would be 7. There'd be 7 electrons in the outermost shell. In comparison to that, sodium, number 11 down here, has 11 electrons to place, 2 in the first shell, 8 in the second, so a total of 10, and then that 11th electron is on the outside there. So the number of valence electrons for sodium is 1. So we've got 7 over here, really just 1 short, and 1 over here, 1 too many. So the idea here is that atoms want to have a nice complete number of electrons in their outermost shell. And so in order to achieve this, atoms have options. They can give up electrons, they can take electrons, or they can be very kind and share electrons. And any of this electron moving about is what we call a chemical bond. And so we're going to talk a little bit about different kinds of chemical bonds, and then specifically about water and how, if we understand chemical bonding, we can actually understand water as a really important biological molecule. I have a hard time with these. I always want to kind of like turn these into people, if you will. And so you'll have to pardon my stories with these. So we're going to start with a kind of bonding called ionic bonding. And ionic bonding comes about because of ions. So ions are atoms that have either gained or lost electrons because they wanted to be happy, they wanted a complete shell. And if ions have an opposite charge, so one's positive and one's negative, then they're going to attract each other. So here it says an ion is an atom, or technically a molecule, with an electric charge because it has either gained or lost electrons. So if it gains electrons, it becomes negative. If it loses electrons, it becomes positive because we know electrons are negative in charge. And that's what this is talking about. Ions are shown by a superscript. And so we had subscripts telling you the number of atoms. Superscripts are showing you the charge on that thing. And so hydrogen with a +1 charge, calcium with a +2 charge because it's lost 2 electrons. And this is actually a molecule that the whole molecule has a negative charge. We're going to talk about these more. These are hydroxide ions. They come up when we talk about acids and bases at the end of this video. So if we do kind of go back to this idea of sodium and chlorine, when we looked at sodium, it had one atom it wanted to, or sorry, one electron it wanted to give up, right? So there's 2, bear with me, there's 8, so we're at 11, or sorry, 10, and one more would be 11. So if it gives this one up, then it's going to have a positive charge. Well, chlorine, so that was my illustration of sodium. Chlorine, on the other hand, has 17. This is going to take me a minute. There's 2, 8, and then 7 in this. I'm only going to draw the valence electrons because it's time consuming. So what happens here is that if we've got this idea of this electron being lost, it comes over to make the chlorine happy. And so chlorine with that extra electron is now an ion of chlorine. And so now we have a positive thing and a negative thing. And the attraction between those two is an ionic bond. And so we talked about sodium chloride before, table salt, as an example. And it is an ionic compound because there's an attraction between these two ions. And again, this sodium, it just wants to give up this electron so that it's happy. And the chlorine is really needy and wants to get that ion. And so that's how they become happy. But then there's this opposite charge, and that's why they come together. Okay, so that's the first kind of bonding. Covalent bonding comes about because I said that there's creative ways that atoms can become happy. And covalent bonds are when electrons are not lost or gained, but they're shared. And so the most classic example of this would be water. And so, oops, oh, sure, I'll go back to blue. I like blue better than red. So oxygen, if I were to draw this out, there's the nucleus. And oxygen is atomic number 8. And so it has 8 electrons to place. So there'd be 2. And then it'd have 6 valence electrons. It would like to gain 2 more. Hydrogen, if I talk about hydrogen, has a nucleus, and then it has just the 1 electron, right? Because it's atomic number 1. And so how this comes together is through covalent bonding. They don't give up and get, but they share. And so in this, if I switch colors again, these 2 electrons get shared, and these 2 electrons get shared. And so this, anything that's held together through covalent bonds is technically a molecule. Not a compound, but that doesn't really matter too much. This idea that electrons are being shared is what makes it a covalent bond. This little video is really just the animation of all that, and I'd encourage you to click on it and watch. On the Moodle site, it's just down below in class. I'll let you watch it. It just makes your head a little bit dizzy watching the yellow electrons zip around. So we've got the idea that we've got ionic bonding, right? So we've got bonding. I always kind of do this in my head. We've got bonds. We can have ionic, and we could have covalent. So ionic is giving and taking of electrons. Covalent is sharing of electrons. Now, there's two different kinds of covalent bonds. We can share equally, or we could share unequally. And so this idea of sharing equally are non-polar covalent bonds. If we were to talk about atoms and their tendencies or their personalities, remember I said like they're kind of needy or they want to give something up and they just want to be happy, kind of turning them into like people characteristics. All atoms have a certain greediness or a certain sort of affinity or an attraction for electrons. And so that's what we're talking about with electronegativity. Specifically, oxygen is a super, super greedy atom. Now, if we have molecules that have only one kind of element, obviously they're going to have the same electronegativity, and so they have an equal amount of sharing. These would be non-polar covalent bonds. So the examples of that would be chlorine gas, because it's Cl2, oxygen is O2, hydrogen is H2, and these are the gases that we can think of. This is chlorine gas that I was saying was poisonous, right? They are non-polar because yes, they're sharing electrons to make them into the molecules that they are, right? 2 atoms of hydrogen, 2 atoms of oxygen, but there's not an imbalance. They have the same greediness or the same electronegativity, and so they share equally. Those are non-polar covalent bonds. These kind of bonds are actually less common in biology than polar covalent bonds, which is what we're going to talk about next. So polar covalent bonds are epitomized by water. And so I said that, and I drew out before that we have water being composed of 1 oxygen and 2 hydrogens, and there was that sharing of those electrons there. Well, oxygen is a particularly greedy atom, and I always giggle because I just like I imagine it as a person almost, or like a kid who keeps all the toys or something. So water has atoms in it, hydrogens and oxygens, with different electronegativities. Oxygen is really, really greedy, and so it keeps the electrons for more of the time, and therefore becomes a little bit more negative. Do you see the negatives here? Right? That's because it's keeping the electrons for more of the time in this unequal sharing of the electrons. Hydrogen, in contrast, is short its electron more often than not because of greedy old oxygen. And so it ends up with a relatively positive charge. And so because these are unequal sharings, this results in a molecule with charged regions, or poles, if you will. So in water, oxygen is a slightly negative area, and hydrogens have a slightly positive charge to them. So this unequal distribution results in polar molecules. And we're going to move on with this concept of polar bonds and polar molecules because there are secondary bonds between polar molecules. It's what keeps your genes together, and it's what makes all of the characteristics of water possible that you learned about in your pre-reading. So hydrogen bonds are secondary. So ionic and covalent bonds are stronger than hydrogen bonds, but hydrogen bonds nonetheless are significant. If we have polar molecules from polar covalent bonding, this secondary attraction between them are hydrogen bonds. And so those neighboring molecules can line up so that the negatively and positively charged regions are actually aligned. So water molecules are electrically attracted to oppositely charged regions on neighboring molecules. So many words. So because the positively charged region is always a hydrogen atom, hence the name hydrogen bond. And I'm not sure if you're the same as me, but I hear words and I read words, but sometimes I just need to be shown a picture. And so this picture, the next slide, is meant to illustrate that secondary bonding, that relationship between neighboring polar molecules where the positive and negative regions line up and they actually attract each other. So hydrogen bonds are important in water's characteristics. So there were a couple videos attached to the Moodle site and the section on chapters 1 and 2. They're both quite good. They do give you a different illustration of this material, and so I'd encourage you to give those ones a watch. You answered this in your pre-reading question. You might not have gone into as much detail, but just to remind you that, the pre-reading is a first pass at this stuff, and the later stuff is really meant to, or like the lecture or the class, the videos is meant to expand that information. So maybe we'll just break out for a short minute here and you can share information about what you wrote about these key characteristics. Okay, we'll do that now, and then I'll go through my explanation. Okay, so in no particular order here, the characteristics of water that are key in biology are density of ice, universal solvent of being water, solvent of life, the cohesive qualities of water or surface tension, and temperature regulation. So different order than are in the notes. If you put them in this order, if you're trying to remember all four, they actually spell duct, like duct tape, not duct tape. You know what I mean? A memory device, but sometimes can just help you organize your thoughts too. So the first one here, when we talk about all of these characteristics, we really want to highlight how hydrogen bonding is related to these. And so it's the hydrogen bonding, it's that stickiness between the molecules of water that lead to cohesion. And cohesion is how literally the molecules stick to each other. It does relate to surface tension because, again, that stickiness of the molecules allow for the water strider to stay on top of the water. It's like it's knit together more firmly so that it doesn't break through. So hydrogen bonds are responsible for surface tension, and it's also this idea of cohesion and plants, how plants get water up their long, tall stems. And so here, this diagram right here, these are the water molecules, and they're linked together with these hydrogen bonds, which allows them to defy gravity and move up. In the kitchen or in biology, when you measure water in a glass container, it actually climbs up the edge. And so this is called the meniscus, and you're supposed to read it from the bottom of the meniscus, because what you're seeing is cohesion or adhesion technically, because it's the water molecule and the glass, but it is a hydrogen bond that's happening with that. And so, significant for biological life, because that's how plants can get water up their stems. And pretty useful for water striders, I'd say too. Or for beautiful dewdrops on the plants or all of that stuff. Okay. The second characteristic that's key here is that water moderates temperature. And I think living on Kootenay Lake or a lot of the water bodies in this area, you are highly aware of how long it takes for the water to warm up. The reason for that, the air is going to heat up much faster than the water because water has a high specific heat capacity. What that means is that it takes a lot of heat energy to actually bring the temperature of water up as compared to other substances. And so there is this moderating effect of living near a body of water. Or if you take a look at the ocean currents, it's the explanation why Halifax is cold and Vancouver is balmy, right? That idea of that moderating effect of that body of water, because water has such a high specific heat capacity. Now, it has a high specific heat capacity, again with those hydrogen bonds, because the heat energy actually goes into breaking those hydrogen bonds before it changes temperature. So this is maybe easier to understand with evaporative cooling. So when you get sweaty, you've got water perspiration on the surface of your skin. This could be the worst diagram ever. So in order for it to evaporate, it has to break the hydrogen bonds that are connecting those water molecules. And so when water breaks those bonds, that heat energy, that energy that is used to break, is taken from somewhere, and it's taken from you. So sweating and the evaporation of that sweat results in a loss of heat energy by you, as the energy is used to break those hydrogen bonds between water. So that energy, that heat energy, goes into breaking those bonds, and you feel cooler. So either of these are significant, same as with the surface tension or water cohesion. Both of those are good examples. So I would encourage you to get your head solidly around maybe one of these and come up with your favorite. Okay, so the third one is that ice is less dense than water. Now, most substances, when they get colder, they become more dense. Water is an anomaly that way. And thank goodness it is, because if ice wasn't less dense than water, it would freeze and sink and freeze and sink and freeze and sink. And the world would soon be a big chunk of ice, maybe. So that idea that ice actually floats on water is a peculiar trait to water itself. So you might have written this into your pre-reading question, that water exists as gas, liquid, and solid, and there's not a lot of substances on Earth. The idea that liquid is the most dense form is a weird thing. And again, going back to the molecular structure, going back to the chemistry on this and understanding it is key. So when water freezes, each molecule, instead of having these hydrogen bonds that are moving around all the time with the neighbors, they get locked into place. They form a stable hydrogen bond. And that three-dimensional crystal structure, that like molecular geometry, if you will, pushes the water molecules further apart. There's more space between the water molecules, and so ice is less dense than water and it floats. So again, with this one, the words are fine, but I love the picture. So this is the idea. This is liquid water with its ever-changing hydrogen bonds between the neighboring molecules. These molecules are free to move around because it's in its liquid state, and they're making and breaking these hydrogen bonds all the time. So as it cools down and there's less molecular movement between these molecules, it gets locked into this solid crystalline structure, and the molecules, again, just because of the bonding angles, are actually pushed further apart. So it's hard to believe, but ice is actually fluffier than water, if you believe me on that. That idea that it's less dense. And again, it's because of the hydrogen bonding and the angles, the geometry of this, and why they get pushed. And that's why they get pushed further apart. So the last one here, and in all honesty, this one is the hardest to roll hydrogen bonding into, which I'm okay with that. So this idea that water is a solvent of life, and we need to go back to the different ideas of bonding here, in that in ionic substances, we have positives and negative things, and in polar substances like water, we have positive and negative things. The idea here is that like dissolves like. So if we have anything that is ionic, it's going to dissolve in water. If we have anything else that's covalent, it's also going to dissolve in water. So if we talk about what a solvent is, a solution has two parts. It has a solvent and a solute. So if I'm making, say, like powdered iced tea, solvent, water, what I'm dissolving stuff in. Solute is what I'm dissolving. And so sugar would be the solute, solvent would be water. So water-based solutions are called aqueous solutions. And because we have, because we're water-based, it's really important that we have things that dissolve in water, because that's how we stay alive. The molecules that make us up need to be soluble in water. So water is a universal solvent because so many molecules are soluble in water. Like I said, you can have ionic substances like salt soluble in water, and you can also have polar substances like sugar or alcohol with the hydroxide group on it, or any other polar molecule will dissolve in water. The idea here that oil, going back to the bonding, would be non-polar. Oils are hydrocarbons, and hydrogen and carbon don't have any oxygen. They don't have any greedy component. They share more evenly. And so this idea here is that if they're not like water in that they have no charged bits, either ionic or polar covalent, then they're not going to dissolve in water. So going back to what I actually wrote, because I kind of get off on tangents, the polar nature of water allows it to dissolve anything ionic or any other polar molecules in it. And really, like I said, all of the biological compounds that we talk about are soluble in water, and that's really important. So this is an illustration of salt being dissolved in water, and you can see how water has these charged bits around it, as do the ions of sodium chloride, and the relative regions attract. And this is how things dissolve on a chemical level. Okay, so we're going to do a small breakout now and put you in some groups, and I would like you to pick your favorite characteristic of water to explain to the other people. So hopefully I'll put you in groups of 4, and we can have somebody on density of ice, universal solvent, cohesion, and temperature regulation. And if you all pick the one, then work together to come up with an explanation of the other ones. I definitely have some that are my favorites and some that are my least favorites. So we'll give you 5 minutes or so to work through that and practice your explanations, maybe probably a little longer than 5 minutes. So the last topic in this chemistry chapter is that the chemistry of life is sensitive to acidic and basic conditions. A lot of what happens in an organism is trying to balance conditions. And so anytime, we're going to talk specifically about acids and bases, but anytime we're trying to balance or keep things the same, we're talking about homeostasis. And homeostasis is that steady state. If we were to talk about acidic and basic conditions, you don't want your blood, for example, to move very far from acidic to basic. You want it to stay steady. And so there's a lot of mechanisms. We'll talk more about those mechanisms that maintain homeostasis in the body. But starting out as an example, we've got things that are acidic and we've got things that are basic. So we're going to start with those in our kind of last topics of chemistry here, in what makes an acid, what it is, what makes a base, and pH and such. You probably have studied this in other courses, so we won't take too long on it. All right, so acids. If acids have a hydrogen ion that come out when it gets dissolved in water, that considers it an acid. And as a simple example, hydrochloric acid, that's stomach acid, is HCl, so it's one hydrogen atom and one chlorine atom, and they come together in an ionic bond. The hydrogen gives up an electron and the chlorine accepts that electron. In solution, it comes apart into hydrogen ion and chlorine ion when it dissolves in water. And so this idea, it donates or contributes a hydrogen ion to the solution. That's what makes it an acid. An acidic solution has more hydrogen than hydroxide. Hydroxide I had written out as an example of an ion that is not a single atom. It's a molecule that has an overall charge. Okay, in comparison or in contrast to acids would be bases. So some chemicals accept hydrogen ions in solution and remove them from solution. Those chemicals are called bases. As an example, we've got sodium hydroxide. So Na is sodium, and then we have this molecule OH. Remember, that had a negative. So sodium is positive, hydroxide has a negative. This is an ionic compound. And when it breaks up in water, it's going to contribute a hydroxide that combines with other H's in solution to make water. So you can see here, 2 hydrogens and 1 oxygen. This reduces the hydrogen ion concentration, and as a result, bases have more hydroxide ions in them than they do hydrogen ions. So they have a higher hydroxide concentration. As an example, if we combine these two, this is a neutralization chemical reaction. So we've got hydrochloric acid, which is an acid, and sodium hydroxide, which is a base. Well, what happens when they mix together is they swap partners. So we have the hydrogen and the hydroxide coming together to make that water. And then we have the sodium and the chlorine coming together to make the sodium chloride. So if chemistry is not your thing and all of these letters make you get confused, you can remember it in words. There's nothing wrong with that. So if you have any acid and any base, it always makes a water, and this is table salt, but any salt. Any metal and nonmetal or any ionic substance can be called or classified as a salt in chemistry. So remember the words, remember the formulas, whichever one suits you and your background in chemistry. Okay, so when we measure acidity, it's on the pH scale. So the pH stands for potential of hydrogen, and it's used to describe whether a solution is acidic or basic. So we've got a pH scale. I know it's on the next page, but it goes from 0 to 14, with 7 in the middle as being neutral. It's a logarithmic scale. So if you've taken Math 12, or remember taking Math 12, what we're talking about is every step along here is a change in hydrogen concentration times 10. So if we were to move from 1 to 2, 2 to 1, there's 10 times more hydrogen ion concentration. If we were to move from 4 to 2, this is 10 times, and this is 10 times. So it's 100 times more hydrogen ion concentration. It's 100 times stronger, moving 2 points down the pH scale. That's what we mean by a logarithmic scale. They're all different by a power of 10, every point along the scale. We want to maintain homeostasis, and buffers are an important way of doing that. There are chemical buffers that help absorb extra hydrogen when things are acidic and absorb extra hydroxide when they are too basic. And buffers are an important way for your blood to maintain that homeostasis, so your blood doesn't become too acidic or too basic. This is a simple example of some things on the pH scale. And like I said, I think most people have seen the pH scale at some point. Yeah, and it's interesting to see. There's a lot more things that are acidic in our diet than there are basic in our diet. Milk of magnesia is an antacid, so it's basic and neutralizes an excess of stomach acid. We think that everything would be neutral when it comes to humans, but we've got saliva and urine that are actually more acidic than neutral, and human blood and tears here just slightly off the neutral. Okay, so last little bit here. You've learned the chemical structure of atoms and molecules gives them their chemical behavior. It describes or explains why they bond or react with other substances. It's really based on their neediness, or if they want to give up an electron or get an electron or share electrons, right? That's what we were talking about in this basic sort of intro to biochemistry and understanding the hierarchy, if you will, behind biology. So we are going to talk about chemical reactions. We've already seen one in that neutralization reaction. So all chemical reactions have things on the left-hand side being added together, and this arrow here signifies the making and breaking of bonds, that rearranging, if you will, into the products. And so we have reactants and products. We have the same amount of things on both sides. We have the same number of hydrogens, we have the same number of oxygens or whatever. You don't create or destroy things in chemical process. You're just rearranging. You're breaking and making bonds, changing the composition of matter. So we've got a few examples here coming up. We've got atoms can combine to form molecules. So hydrogen and oxygen can form water. And so we have hydrogen and oxygen making water. Hydrogen and oxygen are both diatomic. They like to hang out with buddies. That would be a non-polar bond between them. So they always come in pairs. Now, we've talked about how superscripts illustrate ions and subscripts illustrates the number of atoms. Another thing to talk about here are these coefficients. So the fact that there's a 2 and a 2 here is significant in chemistry. If this is your introductory to chemistry, the only thing you need to notice with this is that it allows you to account for the number of things on both sides. So we don't want to create or destroy matter. We're just rearranging it. We're always stuck with 2 hydrogens. Well, oxygen always has, or sorry, water always has 1 oxygen in it. So if we want 2, well, that means we need to have 2 different molecules of water. And if we have 2 here, it distributes. We actually have 4 atoms of hydrogen, and so there's 2 over here. If that lost you, do not worry about it. Just know that these numbers are out here to adjust. They're here to balance so that it's not looking like we're creating or destroying matter. You do not need to come up with those numbers. So there's an example and a bit of a review with the superscripts and subscripts and the way we write things in chemistry. Another example would be a neutralization reaction of an acid and a base. So you can look back in your notes. You can decide, do you want to be a chemical symbol person or do you want to be a word person? So chemical symbol person would be an acid, and as a specific example, hydrochloric acid, and, NaOH as sodium hydroxide, and it would make salt, NaCl, and water, H2O. So if you like the words, you could have an acid and a base, always make water, and a salt. And if you want to balance this one, we've got 2 hydrogens and an oxygen, right? A sodium and a chlorine, and everything is good that way. Photosynthesis and respiration are also chemical reactions. So photosynthesis is where plants derive glucose from using water and carbon dioxide and the energy from the sun. We're not going to cover photosynthesis in this course because it's a human biology course and we don't photosynthesize. But respiration we will cover in excruciating detail in chapter 6. And it's how your body makes usable energy, and that's respiration, cellular respiration. So that really does it for this. There will be another little video that I'll make that explains the rubric for your review pages. So you can give that one a watch. You're now done chapters 1 and 2, so work on those review pages. And then the next chapters, remember you have pre-reading for chapter 3 before you start watching or come to class for chapter 3.